Hello, I would like to share something that has to do with some of the research I've been conducting lately um, for some articles that I've been writing. But there are a few personal thoughts that I would like to share with you guys, and I would be so happy if you could leave me some productive comments and maybe even add some sources to underline your assertions. I'll try and do the same where possible. So, I want to talk about synthetic quantum particles and how it ties into Majorana, fermions, and quantum computers. Do those things even have anything to do with each other? Well, basically, to summarize what I believe all of this research is heading towards and will have to do with is the new particles for more stable qubit states in quantum computers, new materials, super materials that can be developed from the study of these materials, and artificial intelligence in terms of, right now, our machine learning systems run on, you could say, in supercomputer environments, really pushed up processing power. But in the end, it's still linear computing, if you want to put it that way, that's powering our artificial intelligence neural networks. Just imagine you would have these quantum computers in the background. Now, each one being capable of solving or a specific problem. Well, that shouldn't be a problem if you intertwine them and create subroutines. Then basically, this huge, massive, complex could process different aspects needed for a artificial intelligence to be intelligent in an artificial way, meaning, one specialized function could deal with cognitive issues, another one could deal with visual issues, another one could deal with, as I'm just trying to say, because a quantum computer, it's not like a normal computer where you have all these different diverse programs running that can handle and process different problems. Quantum computers, um, as it seems at the moment, are geared more towards um, having a specific architecture that then can solve a specific problem, leaving it at that. But to understand a little bit of the ambition behind people and why they're researching into antimatter and things like that, particle physics, we have to go back to the past where in 1928, um, our empirical science for the first time found that there was another side to the coin. Quote, in 1928, physicist Paul Dirac made the stunning prediction that every fundamental particle in the universe had an antiparticle, an opposite particle, and it was an identical twin but with an opposite charge. And apparently, if these two particles met, so a particle and an antiparticle, they would annihilate themselves, meaning a big kaboom, releasing a poof of energy. Sure enough, a few years later, the first antimatter particle, the electron's opposite, also known as the positron, was discovered, and antimatter quickly became part of popular culture. So, ever since scientists discovered this antimatter and observed the energy it beheld, they wanted to find more of this because energy is a scarce resource and has always been. Beat the energy to do what you want to do throughout the day in a consistent way, or the energy to uphold your systems so that they can do what they do every day in a consistent way. All right, and that even goes down to the scale or up to the scale of particle colliders. They need, the further they want to delve into the space, the deeper they want to fracture space, the harder they have to beat at it. So they really need a punch with a big blow to really fracture space into tiny minute particles that they in return can research. Whether that's a very clever thing to do and really go towards is a question for another debate. So, how do particle physicists and their research relate to quantum computers? Well, let's take, for example, one of the most important phenomena in quantum computers, and it's the qubit coherence. So basically, to perform a computation on a quantum computer, you need to uphold a certain state of your so-called qubits. That and that state has to be upheld long enough for two such, you could say, qubits to communicate with another, and thus creating some sort of logic gate. You know, you need that to compute. But unfortunately, up until today, um, as publicly noted, the time these particles or qubits can actually stay in this um, coherent state, meaning they're not zero, they're not one, they're basically Schrodinger's cat in the box in that moment. So they're both one and zero. That's basically qubit coherence, and the time they can stay in that state is very limited um, these days, especially because there's a lot of things that interfere on that level. You know, when you sit at the table, someone drilling in the back doesn't really throw you off your socks. But if you were to be a little leaf, just the slightest wind will blow you away. Now, just imagine you are something as minute as a quantum particle. You know, we're talking about background radiation just being your wind and blowing you away, or interfering with whatever state you're in. So, how to increase the qubit lifetime? The lifetime it takes the qubit to decay from a quantum superposition of states to a classic state. This is the question they ask. How can we increase this time? Because the longer we can keep this qubit in its state and prevent it from decaying into a quantum superposition, from the quantum superposition into the classical ones of either being 1 or 0. The longer we can keep it in a quantum superposition, the more operations we can conduct. So, particle physics, to connect it, is actually also helping us develop quantum computers and quantum computing, because in the future, you see these processes get more and more complex. So you can't have humans calculating whatever's happening there, because when it happens in minute moments. We're talking about thousands, millionths of a second, and to actually work in that sphere, there's a point where we can't use normal computers, because if we take a normal Pentium, let's say a 2000 operations, 2.8 gigahertz, that means 2.8 giga million operations per second. Okay, so it can detect 2.8 million operations per second if you totally dedicated to do just that, because at the moment everything that happens on the computer that needs logistical coordination takes one operational piece of your computer. So let's say, for example, of your 2800 um, gigahertz per second, a certain amount is going towards working your memory, another part is going towards managing your hard drive, your programs that are running, and so on and so forth. Okay, so that's how it's split up. So you need a really specialized and focused computer system to measure these things happening, and at the same time control everything logically. So wouldn't it be the most logical conclusion instead of using humans to use a supercomputer or a quantum computer even, um, and put an artificial intelligence on top of it? A lot of people are just aware of the particle colliders in CERN and maybe a handful in the United States, but the reality is there are particle colliders in Eastern Europe, Russia, Siberia, probably even Japan, France, Germany, Italy. I wouldn't be surprised if there were any in Portugal, um, the Americas, of course, and who knows, maybe even in Africa. Whilst I haven't really heard anything yet, but um, this one is an example. In the top right, you see the two big rings. It's the whole complex is the Fermi Labs Accelerator Complex, and it accelerates protons to high energies and then sends them out to to other receiving stations where they measure these things. And down in the bottom right, you have an example of a linear particle accelerator, which this one is from Stanford University. And back in the days, there wasn't always the ring accelerator as we have it now in terms of it being a standard. In the beginning of the research with these things, they were playing around with the idea of having these straight lines. Because they thought, like, hey, I mean, just propel it on a straight line and crash it against the wall. I mean, that's what a bullet does, right? You stand, aim, and pull the trigger. But as they noticed that there's more to this, and you need ever more energy to create ever larger or more minute scatterings of our material dimension, they came up with these ring collider models where there's usually one smaller ring that brings the particles or the beam up to speed, accelerates it, like kind of pre-accelerates it, and throws it into the larger ring where it gets super accelerated. To the left, you actually see this is a picture. The bigger picture is an example of um, the the ring tunnel inside of the LHC, and that's inside of this, looks like a pipe. um, it's basically sealed and hermetically sealed and surrounded by superconductors and magnets. So scientists at places like Stanford seem to have found a way to synthetically create particles that could potentially be used for quantum computers or making them more stable. Quote, in a discovery that concludes an 80-year quest, Stanford University of California researchers found evidence of particles that are their own antiparticles. This means that the particle in a certain state becomes its own antiparticle. You can just imagine basically like spinning a top, one to the right and the other to the left. When they bounce against each other as they're turning in different directions, they kind of become a particle and an antiparticle in the way they affect each other, although it's the same type of spinning top. So these particles are called Majorana fermions, and they could one day apparently help make quantum computers more robust, says the scientists at the Stanford University. So what these scientists are basically doing is using certain superconductive materials and researching with them, throwing particles at them, maybe even um, to produce other synthetic particles that do not occur in that particular way in our natural environment. And so physicists have thought for a long time that Majorana fermions could arise out of the types of materials used in those experiments. But they put together several elements that had never been put together before, and engineering things so this new kind of quantum particle could be observed in a clean, robust way in real is a real milestone apparently. So these people, it's basically saying it here, are creating artificial or synthetic materials um, that they in return create from actually using antimatter and matter reactions, you know. And I want to come to this in the end because even though we say that antimatter and matter extinguish each other, but then again, there's circumstances when they harmonize where they create a third neutral particle, which we then usually know as what we have. Like you could say we're the neutral zone, the friction zone. Um, because then there's the one side and the other side when you tear it apart. You could see it as a hurricane or tornadoes or things like that. So, but basically, why are the colliders always being um, built underground? So, why are they being built underground? Well, one reason is to eliminate the background noise. The problem with these experiments is that they happen at such a microscopic scale that things like cosmical radiation can interfere with the results. And that's why scientists try to go underground, very deep underground. And there are numerous deep underground research facilities around the world, which, if you like, I can talk about in a future presentation. And their websites usually say that what they're doing has to do with the research in antimatter and high energy physics and other things. Plus, they probably believe that whatever happens underground is less likely to affect the surface environment and will be thus contained in the underground environment. Particle colliders are used to find supermaterials. Well, colliders and material research. The European Free Electron Laser X fell in Hamburg. I just want to bring this up because I want to kind of support what I just said, that these scientists are actually also using these colliders to find new materials. And there's this report I found on superconductive France um, about colliders and material research. It says the European Free Electron Laser X fell in Hamburg and the Spallation Neutron Source ESS in Lund that are currently under construction will soon use superconducting RF cavities to economically accelerate beams, respectively electrons and photons. Now here it comes, that will produce intense X-ray and neutron beams to study materials, living molecules, and condensed matter. Yeah, so there's in this presentation already you have these diverse uses, numerous uses of these collider rings. They're more than just splattering particles against the wall. That's what we've always been believed they're doing, and every now and then when they scatter it hard enough, they come back at us and say, "Hey, we found a particle," and then we're like, "Woohoo!" We have no idea why and what we can do with it, but hey, it's something new, and then we forget about it. And if we ever hear particle colliders, our head says, "Bump, oh well, it's scattering particles against the wall to figure out what the building blocks of matter are. But there's more to it, people. Do your research. Go beyond YouTube. YouTube is a great resource for inspiration, but if you want to be firm on whatever there is, there's no problem. Just go out there. Even if it's your favorite show, whatever that person says, if he's legit, he'll be honest that that's his opinion, and some of the things are still open for debate. So you go out there and you verify what anybody says. And in that process, you learn about it, and you come back to YouTube like I'm doing right now, and you share whatever you find, okay? And that way we grow, we become hive mind, like something that's unique in each of its elements, but forms a singularity in the bigger scope of things, and we've been that before there's been any supercomputers. I just want to say that now, so it's not like we're not gonna copy something that's coming up in the future. No, we're copying ourselves. We're copying, as a matter of fact, no matter what we invent, we're copying the universe. It's already there. We're just creating it with the garbage we have down here. So just to um, relax your mind with some images and concepts that might help us think. It's so easy to always just think in good and bad. However, these things usually manifest at the same time, and they have a relation to one another. And as soon as there's an imbalance of one, um, the other one gets too strong, or the coherence breaks apart. For example, in radioactive materials, most elements have the same amount of particles inside of their core, inside of the nucleus of the atom. Sorry. So there's the same amount of, you could say, positive particles there as there is the negative particles on the outside of the atom, electrons. And if there's an imbalance, then the atom starts decaying, right? So inside of the nucleus, there's these neutrons and positrons. One is neutral, so to say, and the other one is the positron. So that's the balance of the nuclei. And the nuclei itself gets balanced by the electrons in the outside. But if between those neutrons, the neutral particles, and the protons, the positive particles, there's an imbalance, then that whole structure starts falling apart. So that's how we get radioactivity. Another example of how opposite forces play together in nature to create something that we are familiar with are hurricanes. If you look at the picture in the upper right corner, you'll see that a tornado or the likes is, as we know it and as we look at it, seems to be a phenomena. Okay, it's just there. Oh, there's a tornado. We say tornado. There's no plus and minus to tornado. It's not like we say, oh, look, there's a yin yang symbol. You see, they were saying there's a plus minus symbol, all right? But we just say tornado. And most people don't know that this phenomena is actually a combination of hot air pushing down, sorry, cold air pushing down, and hot air pushing up. And this phenomena creates a whirl and a turn, all right? And in certain terms, you have those strong winds that move and push everything, but the turning force comes from the cold air pushing down and the hot air pushing up. And I'm sure that goes on into whatever examples we have. I mean, when I look at a galaxy, I can't help but think of the milk in my coffee in the morning when I mix it with a teaspoon. I can't help but think of tornadoes, how they look like from space. I can't help to think but about our galaxy, how it probably looks like in 3D moving through the solar system. I know it got a little bit out there, But in a certain way, it's all interconnected. And every time we try to step out of the interconnection and put us above it, we create havoc. So I just wanted to create this holistic type of presentation, for the lack of a better word. I wouldn't know how to call it. Okay, I hope this wasn't confusing or anything. And if it was, just watch it again or watch it 2 times, and I'm sure you'll be able to distill some interesting information from it. I did while I was doing it. And thank you very much for watching. Go ahead, please support what I do if you like it. Um, it will motivate me a great deal if you like, share, and subscribe to my channel. Um, with that being said, take care and best of luck